Okay, welcome to another demo from the Moving AI website, from the demos and other videos that we have here. And today we're going to be looking at a demo of a star running on a map. And this is a little bit different than some of the other videos that I've been recording differently, because on the previous videos what we had was we could build ourselves a graph and we could look at the edges and the h-costs on the nodes during the search, and we could sort of step the search one step at a time and watch what happened with the open list and other data structures. Here what we're going to see is we're looking more at a high-level overview, so with a much bigger picture of what's going on. And as we look with that overview, we'll be able to observe things from a different perspective. Now, this demo has got a few new features. They're few as of the recording of this video. Over time, of course, these will be old features, but and they may continue, of course, to evolve over time. But we put some features in, or I put some features in here. One is that the feature was sort of here, but it wasn't well tested, and so I didn't deploy it. But we can resize this viewport now. So if I make my window be larger, then the size of the demo inside the window will scale according to the window. And I can go here and make this demo be quite a bit larger as we go into this window. So this is great if you want to be able to look a little bit closer at what's going on. You can get your window to be larger and see things more clearly. The other thing that I've done is I'm at least testing for the time being. So this isn't deployed yet, but it'll be deployed soon. I just have to do some testing. But I didn't want to record a video on the old version of the code before and then release it on the old version if the new version was almost here. In a lot of the demos, I've got buttons down at the bottom here, and those buttons are used for controlling the demo. Here what I've done is I've extended this frame over slightly and put a new little user interface here that's going to allow me to do my control from the side here. This gives me a little bit better feedback between what was being controlled basically by JavaScript before, and now what's sort of more integrated into the application. So inside this application, we have a map here. We can choose between different maps. This is from a map from Dragon Age Origins. This is a map that I worked extensively on when testing. So these are bedrooms inside a mage tower, and this, I believe, is a library. I think there's an entrance where you come in here, you come through, and then you go up some stairs here to go out to the next level. And this is from Baldur's Gate 2. My colleague was the one who extracted this map initially, and then I released this more broadly as part of the Moving AI benchmark problems. On here, we can choose between a number of algorithms. So I've got Dijkstra's right here. I can choose a point, and I can drag between 2 points here. It'll mark the start and the goal, and we'll do the search. The green nodes are on the open list, the red are on the closed list, and the yellow node, which we can't see too often here, but if I were to if I just watch here, I can see the yellow node is the next node to be expanded at any step. And okay, so that's running here, and I can choose between Dijkstra's, A star, weighted A star with a weight of 2, weighted A star with a weight of 10, and I can choose my heuristic between octile, which is a heuristic that takes into account the fact that we can only move horizontally, vertically, and diagonally on the map. And so the heuristic is computed accordingly, versus Euclidean, which is a straight line heuristic. And then differential heuristic is a heuristic that uses the triangle inequality, and it builds an embedding. It is designed for undirected graphs versus alt, which is designed for directed graphs. We can choose how fast the search goes, so we can see it's going fairly slow here. If we want to animate a little bit faster, we can speed up the search. And we can also choose to turn node reopenings on and off. And we'll talk about that in a second. When we're done, then the path is drawn here in a thick blue line. So here's some of the things we see. In the previous demo, or if you're still looking at the previous page, node reopenings isn't, well, it was always an option in the demo, but there was no interface to control it. And so I exposed that interface here to make that available. So let's go through and just talk about some of the many different things we can observe by looking at the different algorithms. We'll start with Dijkstra. We'll work our way then through A star and weighted A star. And on each of these, there's great discussion points if you're teaching a class about these different things and what the behavior looks like. So let's just start with Dijkstra's algorithm. One, we can think about with Dijkstra's algorithm, do I need node reopenings? So this is when, if I find a shorter path to a node that I've already expanded, then node reopening says, hey, I'll take that node and I'll reopen it with a shorter cost that I found. And so the question is, well, does Dijkstra's algorithm need reopenings? And the answer there is not initially, and not on this problem. And the question is, well, when would Dijkstra's algorithm ever need reopenings? Could it ever find a shorter path to a node that is already expanded? And the answer is that with positive edge costs or even zero cost edge costs, then that shouldn't be a problem. However, if I have negative edge costs, and let's assume no negative edge cycles, then it is the case that we could, with Dijkstra's algorithm, re-expand a state. On this problem, we don't have negative edge costs, so we're not going to see that. But there are, again, other demos that look at some of the things that are related to that. And some people mistakenly think that Dijkstra's algorithm doesn't work on graphs with negative edge costs. In fact, as long as you do reopenings, there's a paper that describes this, I think from the 70s, maybe in the late 60s, but that says that, look, as long as Dijkstra's algorithm does node re-expansions, it'll be fine. It's guaranteed to do single source shortest path, but the number of re-expansions could be prohibitively large, and so we've got to be careful about that. A couple of other things we could observe, so I'm just going to turn reopenings off for right now. We'll do 1,000 nodes. And is that Dijkstra, we know, is not a goal-directed algorithm. So does Dijkstra do anything different, at least if we think about the search? So I do a different number of nodes as I search to a different goal. But if we think about the structure of the search, so looking at the order in which nodes are expanded, does Dijkstra change as I change my goal? And what we notice here is as long as I keep the same start state, then the order in which nodes are expanded, Dijkstra doesn't change its behavior at all. And therefore, changing the heuristic isn't going to make any difference at all either here. Okay, so that gives us Dijkstra's algorithm, and we can see node re-expansions here. Let's go ahead and move to A star. So what is A star doing, right? It's now looking at both the cost, the G cost, plus the heuristic, and we have some different heuristics here. And now we can look at the same thing. Well, will A star change its behavior based on where the goal is? And now we can see that A star is going to get very different behavior based on where the goal is, unlike Dijkstra's algorithm, which had the exact same behavior no matter where the goal was. Okay. So we immediately can see that difference, and we can see how much more efficient if we compare back and forth between A star, let's go even bigger here, between Dijkstra and A star. And in general, we could ask, are there any cases where A star might be worse than Dijkstra's algorithm? Could we think of that? So there's an interesting question. And it ends up that there are a couple answers where Dijkstra's algorithm could be a better algorithm to use than A star. One would be if you have an inconsistent heuristic. There are some cases where this can happen. Again, this demo isn't going to showcase that, but we do notice that we don't need to do any reopenings here, and the reason why is because our heuristics are consistent. But if we have an inconsistent heuristic, for instance, a compressed differential heuristic, then reopenings could be expensive if we don't take care of them with something like BPMX. And it ends up then that Dijkstra's algorithm could be better than A star. The second case we could look at is if you're running A star and you had, for instance, a very, very, very expensive heuristic. Just that requires a lot of computation. Maybe you're doing sines and cosines or other operations like that that are not inexpensive to do. And but yet you didn't get a very accurate heuristic. Okay, so if I got a heuristic that was very expensive and not very accurate, then although A star may expand fewer nodes, it may not actually be faster in practice. So we have to be careful about the cost of using this heuristic versus the cost of doing the search. Okay, so some other things we can look at then is the difference in different heuristics that we can use. And we can ask the question, like, why, what is the difference between using octal versus Euclidean? In fact, if we look at the same problem, what we notice here is that Euclidean is going to come straight across here, and is gradually expanding out here the state space. And that's a little bit different behavior than we get for octile heuristic, where we actually fill this in going across here. So we could ask, what is causing that difference in behavior? Why does Euclidean get this sort of much smoother behavior of expansion outward versus octile heuristic, which is giving us very much a filling in behavior of the search? And the answer here has to do with basically Euclidean distance assumes that we're not on a grid. And so we can get this sort of straight line. We think that there's a straight line path that exists, even though we can't take that straight line. And so even on some very simple problems, so we can get very, very simple problems here. Let's see, I need to get a little bit off here. So fairly simple problems, octile is going to go straight to the goal. It's with this diagonal plus cardinal. So for this, the octile heuristic is perfect. But we can see here that the Euclidean heuristic, and I'll slow it down, the Euclidean heuristic is not perfect because it thinks we can go straight to the goal. We can't actually do that. And so it considers like, well, maybe I want to go out to here somewhere because at that point, I will then be able to go straight to the goal. We also notice that the path that's found by Euclidean here is a very different path than the path that's found by the octile heuristic. And so there are some things that you can do, for instance, where you might tie break to try to extract a Euclidean path, which is a little bit more of a straight path versus an octile path, if you were dealing with grids in practice. And we can see the impact of a heuristic, though, right? So it makes a big difference when we think about really hard problems. When I use something like the differential heuristic, there's a massive difference in the work it requires to solve the problem. Okay, with the octile, so we see a small difference between octile and Euclidean on this particular problem. Differential heuristic is a massive difference. Okay, so that's some things we see with A star, and there's some things we'll look at on the other map in just a minute with weighted A star. But let's go ahead and move to weighted A star. And so here we can start to think about, for instance, looking at the different paths that are found by weighted A star versus A star. And we know weighted A star with a weight of 10 should be, weighted A star with a weight of 10 should be able to find, has this ability to find lower quality paths. And weighted A star with a weight of 2 can only be 2 times suboptimal. Now, any path we find here for both of these algorithms is going to be within both of those bounds. But we're going to see differences in the paths that they find. And so let's speed this up a little bit. And so what we see here is weighted A star with a weight of 2 gets this path here. But when I move my weight to 10, I get actually a very different path, or a little bit different of a path. Let me pull that out here. So weighted A star with a weight of 10, the path comes diagonally here and then comes across here and around. With a weight of 2, we get this path that looks here. And so we could ask that question, why is weighted A star a weight of 2? I mean, it does have a lower suboptimality bound here, but this path is not twice as long as the optimal path. So why is weighted A star with 10 finding this path that looks this way versus weighted A star with a weight of 2? And the best way to understand this, so yeah, I mean, all of these things you can pause and think about them, but the best way to understand it is if we go with a weight of 1, what we see is the path comes straight down here, and then we're gradually expanding this path out here, and we're not going to be doing anything to update that path. So as we gradually expand it out and come around this corner, then the first node that I expanded coming out, the path did go down and go across here. And so if I finish that off, you see, there we go. But when I look with a weight of 2, what we actually see is I come down here, but I'm going to keep expanding these paths from higher up in the path. So because weighted A star of 10 is more greedy, then it comes straight down here, and then it sort of pushes out the expansions going across, where with a weight of 2, we tend to keep expanding from higher up. And as a result of that, then we get this path here. Now, could we do anything maybe to change this behavior of the path that we're finding? And the answer actually is yes here, and this has to do with node reopenings. So although our heuristics here are admissible heuristics, when I use weighted A star, and they're consistent heuristics, when I use weighted A star, I'm weighting that heuristic, and weighted A star implicitly is actually making the heuristic inconsistent. So on that problem, then, or the other way of thinking about it is that we're dividing the g-cost by 2 or dividing the g-cost by 10. So the heuristic is vastly overestimating, so it's not only inadmissible, but it's also inconsistent. And when we think about that, then, those are the cases where we can actually do node reopenings. So let's go ahead here and solve this problem again and look at node reopenings. And what we see here is that as weighted A star searches, it does find an initial path here that's not the optimal path. And so after it finds the path, so it's actually going down and back up, then it's actually improving this path here. And this is why we're seeing some node re-expansions that are occurring with the purple nodes here. And we'll speed this up. We're going to see some more re-expansions there, and we get to the goal. So this happens. We're basically finding the same path here. So they didn't really benefit us a lot, but they did cause us to do some extra work. If we run with weighted A star with a weight of 10, though, slow this back down again, what we see is that as this path goes across here, every time we come down this main portion of the path here, we're going to do some re-expansions back into here. And the result of that, speeding the search up, is that when we're done, our path actually has been shortened. So we can see with weighted A star, with weight of 2 or weight of 10, that we can actually get a shorter path by significantly short. Well, we've cut off this corner here by having node re-expansions on versus off. So that gives us a much better path. But we've got to ask the question, what is the cost of this? And so an interesting question then is to say, can we choose some problems here where we might see a big difference in the number of re-expansions we do, that the re-expansions are really causing us a lot of problems when we're using weighted A star. And we can see here for many, many different problems that, there's a few re-expansions that are done. It's not a big deal. And so, we don't really mind paying maybe a little bit of that cost to get a better path. And but there's other problems here where I'm going to show something like this, and we'll speed things up. Actually, let's do that again, just a little bit of a slower speed. Here we see we're going to go back through here quite a few times, and this looks like it could actually be getting quite expensive here. It's going to be a lot more node expansions than was done by when we didn't have node reopenings, and because we just went through and expanded every node once. And the path quality in this case isn't that much different. So if we look, we turn it on, we turn it off, we get a slightly better path, but the number of node expansions we do when we turn it on is that we're doing a lot more node re-expansions there to solve the problem with it on than with it off. And so there's something we can explore here to try and understand what's going on. And there is another demo on the web page that shows the difference of how bad re-expansions can be for weighted A star if we have them on. And of course, do we have to keep them on or off, which is dealt with elsewhere. Okay, so we've seen some things here with weighted A star and A star. Interesting question then is, can we find problems where weighted A star, perhaps with a weight of 10, is going to do worse than weighted A star with a weight of 2? We are able to create that on artificial graphs, but can we create that on other problems as well? And here, when we think about this, well, we definitely see if we're turning node reopenings on, then weighted A star with a weight of 10 can be much worse than weighted A star with a weight of 2. And because weighted A star with a weight of 2 is going to tend to find better paths initially, it may often do fewer node re-expansions. Now, I'm not printing right here the exact number of node expansions. Maybe that's something I'll add to the demo at some point, so we could actually measure that and see the difference. So the last thing I want to look at is just to go over to a different map here. And this is something that you can see with A star, but you cannot necessarily see really clearly. But something about the shape, thinking about what is the shape of the open list and the closed list when I'm using different heuristics. So Euclidean, speed this up, versus octile. It's hard to see a really clear difference here between these two heuristics, although if we're going really fast, then we can see a difference, like in the amount of work that we do Depends on exactly where the start and goal are. But so here we see with Euclidean, we filled in all the states around here, and then there's some dividing there. If we are using the octal heuristic, then we've not quite done as much work. But there's something that we can actually see really, really clearly with weighted A star with a higher weight, and it has to do with the shape of the open list. So if we watch this going out, we can see the shape of the open list is defined by these sort of diagonal, and then a piece here, and a diagonal, and then another piece there. And it's almost like there's a portion of an octagon that's being created here as we go out. And so we see that sort of very clearly with the behavior of, and here we can, weighted A star with a weight of 10, right? We see this very clearly as we go around here. And when I use Euclidean distance, I actually don't see that behavior. What I see much more of is much more of a circle. And so the interesting question is, why is this the case? Why is it that, well, one, with weighted A star weight of 10, we see very clearly a circle here, where with a, when I run A star, I won't actually see that clear difference between a circle going out. So let's run A star. It's a little bit harder here to see the difference. Like it looks fairly circular there. When I run octile, it still looks fairly circular. So why does weighted A star give us this much more octagon shape coming out? And then Euclidean gives us a much more circular shape. So that's a question to think about. There's maybe technical details, or there are some technical details of an answer of why that's the case. So I'm not going to develop it in this demo, but it's something that we can observe here. We can think about and use it to understand the nature of these algorithms. So what we can see here, and we can turn node reopenings on, we can see on this particular problem, there actually isn't a huge number of reopenings that we get, even with weighted A star of a weight of 10. So you can think about, well, why on some problems, in some areas do we see a lot of re-expansions, and other areas we don't. So there's a lot here we can play with at a really high level to look at these demos, to try to understand the behavior, get a feel for the behavior, and to look at the algorithmic components, the decisions that are being made, and understand how those impact what is going on here. So hopefully this is useful for you to just get a good handle on understanding these algorithms and being able to play with them. If you're a teacher or student, hopefully these are great for your learning. And thank you for watching. And we'll look. This won't be immediately deployed, but should be deployed soon to the main Moving AI webpage. And we'll look at some of these other interfaces getting updated. But we'll look forward to seeing you in a future video. Thank you for watching.